Hi, everybody. Before we dive into groups from a formal point of view and actually give a mathematical definition of them and start talking about their properties in an abstract way, it's good to nail down two examples, at least, of things that are groups so that the whole process doesn't seem hopelessly abstract. And the first of those examples is something that you should have seen before in your other math classes, certainly in Math 2710, and that is the integers mod n. So let's give a brief refresher about the integers mod n, and then take a look at them sort of from the point of view that we'll be taking in this course. So to start, we fix an integer n, which is bigger than 0, and we introduce a relationship between integers. We say it's a relation on the set of integers. We say that two integers a and b are congruent modulo n, and we write that with this a congruent to b mod n notation. If their difference, if a minus b is a multiple of n. So just by way of example, if n is 2, then a is congruent to b mod 2 means that a minus b is divisible by 2. In other words, that a minus b is even. And that happens in two cases. A and b are both even, or a and b are both odd. Because if you're even, then your difference is even. And if you're both odd, your difference is odd. But if A were odd and B were even, their difference would be odd, which isn't a multiple of 2. So the relationship A congruent to B mod 2 could also be expressed as A and B have the same parity. But, of course, we can work much more generally, and if n is 5, then we know, for example, that 7 is congruent to 2 modulo 5, because 7 minus 2 is divisible by 5. And similarly, if you take any number of the form 2 plus 5k, where k equals an arbitrary integer, then m is going to be congruent to 2 mod 5. So the numbers which are congruent to 2 mod 5 are the arithmetic progression, which starts with 2 and takes steps by 5 in both positive and negative directions. So the set of x such that x is congruent to 2 mod 5 is the set, well, let's see. It's going to have negative 3 in it, and it's going to have negative 8 in it, and it's going to have negative 13 in it, but it's also going to have 2 in it, and it's going to have 7 in it, and it's going to have 12 in it, it's going to have 17 in it, and so on. So it's this arithmetic progression that goes off in each direction. And this relationship is an equivalence relation. So just this is part of the prerequisites for the course, but just as a quick reminder, an equivalence relation has 3 properties. It has to be symmetric, reflexive, and transitive. And here, reflexive means that every element is equivalent to itself, and that's certainly true. A is congruent to A mod n for all A, because A minus A is 0, and n always divides 0. It's symmetric because if A is congruent to B mod n means that A minus B is kn for some k. It's a multiple of n. But then B minus A is minus k times n. In other words, it's also a multiple of n. So B is congruent to A mod n. And as is usually the case, the transitive one takes a little bit of thinking. Transitive means that if A is congruent to B mod n, and B is congruent to C mod n, well, then A minus B is kn, and B minus C is, let's say, tn for integers k and t. And then if you look at A minus B plus B minus C, well, on the one hand, that's equal to A minus C, but it's also equal to kn plus tn, which is k plus tn, which is a multiple of n. So A is congruent to C mod n. And that's the transitive property. So the congruence relation is an equivalence relation. Now, if you have an equivalence relation, you can divide a set up into equivalence classes. And in order to see how that's going to work out, let's first start by remembering the division algorithm. So the division algorithm is basically division with remainder, and it tells us that every integer a can be divided by n, and it yields a unique quotient and remainder. And the quotient and remainder satisfy a is q times n plus r, where r is between 0 and n. So, for example, if n were 2, this says that any integer, like 7, can be divided by 2 with a quotient of 3 and a remainder which is either 0 or 1. And in 7's case, it's 1. And in 8's case, it's 0. Or if n were 5, then every integer can be divided by 5 with a remainder of 0, 1, 2, 3, or 4. So here are a few examples. And this can be a little bit annoying if the number is negative, but it's still true. So for instance, negative 11, you might guess that the quotient is 2. Negative 2 times 5, which is negative 10. But then you'd have to add negative 1. And that's not allowed, because if you want the remainder to be between 0 and n, what you actually have to do is write negative 11 is negative 3 times 5, which is negative 15, and then you add back 4. And now your remainder is between 0 and 5. So the division algorithm works perfectly well for negative numbers, but sometimes the quotient isn't exactly what you would expect. And of course, this is closely related to the notion of congruence, because if A is Qn plus R, that tells us that A minus R is Qn, and so A is congruent to R mod n. In other words, every integer is congruent to a unique integer r between 0 and n minus 1 inclusive. In other words, there are only n possibilities for the different congruence classes. If you take a number mod 5, it's got to be congruent to 0, 1, 2, 3, or 4. So there's only 5 possibilities because it's always congruent to its remainder when you divide by 5. So I've just restated that here. Every integer a is congruent to exactly one integer r that satisfies r bigger than or equal to 0 and less than n. And this is what you would expect for an equivalence relation, because an equivalence relation always partitions a set an equivalence relation on a set X always partitions X into disjoint subsets. So each subset is of the form you pick an element of X and you take everything which is equivalent to it in X. So my equivalence relation here is called R. And each of these sets X has the property that first of all, they are disjoint from one another. In other words, X and Y, X and Z, let's say, are equal if and only if X is related to Z. Otherwise, they're disjoint. And that's written very abstractly, but what it means in the context of congruence is that if we fix n, let's say n equals 5, then we have the classes 0, 1, 2, 3, and 4, and every integer belongs to exactly one of these. So that's just a fancy way of saying that you can only be congruent to exactly one number, but if you're working mod 5, between 0 and 4 inclusive. So you're always congruent to your remainder. So for instance, 13 is in the class 3, and negative 11 is in the class 4. We did that calculation up above. And there's no number that's in the intersection of the, you can't be congruent to both 2 and 3 mod 5. If you were congruent to both 2 and 3 mod 5, then by transitivity, you'd have to have that 2 and 3 were congruent mod 5, which is clearly not true because 3 minus 2 is 1, which is not divisible by 5. So now finally we can talk about arithmetic. And we define the sum of the congruence classes mod n just by saying that the sum of the congruence class of A and the congruence class of B is the congruence class of A plus B. And what this says, let's look at the case n equals 2. What does this say? So when n equals 2, there's only two congruence classes. There's the class 0 and there's the class 1. And this is the collection of even numbers. If you're congruent to 0 mod 2, then you are divisible by 2, so you're even. And this is the class of odd numbers. If you're one more than a multiple of 2, then you're odd. And if you take any even number and you add any odd number to it, you always get an odd number. And that's what this statement 0 plus 1 equals 1 means. This means that if you take any number from the collection 0, which means any even number, and you take any number from the collection 1, that means any odd number, and add them, you always get an odd number. And that's what it means to say that this is well defined. It means that it doesn't matter. I don't have to pick 0. I mean, this is a set, and it contains all the even numbers. So it's, for instance, true that 0 is equal to 14, and 1 is equal to 11, because the collection of numbers that are congruent to 14 mod 2 is the same as the collection of even numbers. And so that's okay, because 0 plus 1 is also equal to 14 plus 11, which is 25, which is 1, because no matter what even number I pick and no matter what odd number I pick, when I add them together, I still get an odd number. And in the case where, let's say, n equals 5, if you take the class of 2 and the class of 1 and you add them together, by this definition, you should get the class of 3. What is this telling you? It's telling you that any number congruent to 2 mod 5 plus any number congruent to 1 mod 5 is always some number congruent to 3 mod 5. In other words, take any number which has a remainder of 2 when you divide it by 5, and any number which has a remainder of 1 when divided by 5, and add them together, you're always going to get a number with remainder 3 when divided by 5. So congruence arithmetic is really remainder arithmetic. What you're really doing is you're just keeping track, when you add numbers together, of what happens to the remainder. Similarly, if you take a number 2, which has remainder 2 when you divide it by 5, and you add a number which has remainder 4 when you divide it by 5, well, by the definition above, this is 6, the class of 6. But the class of 6 is the same as the class of 1. And so if you take a number which has remainder 2 when divided by 5, and you add a number which has remainder 4 when divided by 5, you get a number with remainder 1 when divided by 5. So this congruence arithmetic, let's just look at the 3 special cases. We've sort of already done this, but we can, for n equals 2, we can make a little addition table. We have only 2 congruence classes mod 2, 0 and 1. And let's look at what happens when we add them. Well, if you add 2 even numbers, you get an even number. If you add an even number and an odd number, you get an odd number. If you add an odd number and an even number, you get an odd number. And if you add 2 odd numbers, you get an even number. So this gives us a set which has an addition operation. The set has only 2 elements, and it has an addition operation. We call this z mod 2, or z mod 2z, meaning the integers mod 2. And we can do a kind of algebra here, a very simple kind of algebra where there's only 2 elements. If we want to do this for n equals 3, now we have 3 classes: the numbers with remainder 0, the numbers with remainder 1, and the numbers with remainder 2. If you add a number with remainder 0, nothing happens. If you add a number with remainder 1 to itself, you get a number with remainder 2. If you add a number with remainder 2 to itself, well, you get a number with remainder 4. But that's not really a legitimate remainder. Maybe I should say more precisely, you get a number that's congruent to 4 mod 3, which means it has remainder 1 when divided by 3. And that's because 2 plus 2 by definition is 4, but 4 is congruent to 1 mod 3. So this is actually equal to 1 again. 2 plus 1 is 3, but that's 0. and 1 plus 2. And one thing to notice about this is that these operations are commutative. Namely, if you add 2 plus 1, it's the same as adding 1 plus 2. And that's kind of clear because if you use the definition A plus B equals A plus B, it's also true that B plus A is B plus A, but B plus A equals A plus B. And maybe just for the sake of completeness, let's look at n equals 5. Takes a little more writing. We have, and now I'm just going to drop the boxes so I have use up less space, but you should understand that there's a box here. So when you add 0, nothing happens. When you add 1, you get 2, 3, 4. Now 4 plus 1 is 5, but the remainder class that corresponds to 5 is 0, so we would write 0 here just so if we add 2 plus 1, we get 3, 4, 0, and then we have 2 plus 4 is 6, but 6 has remainder 1 when divided by 5. Here we get 4, 0, 1, 2, and then we get 0, 1, 2, 3. And this is the addition table for this, just to get the notation right, this is Z mod 3Z, and this is called Z mod 5Z. So for every integer, we have the collection Z mod NZ, which is a set with n elements, which has an operation on it, which we can think of as addition. And the only bizarre thing about it maybe is that we're working here with classes of numbers, and we have this weird situation that, for example, 6 is equal to 1 in Z mod 5. And maybe one way to, this may seem odd that you can have multiple names for the same thing, but actually if you think about the way fractions work, it doesn't bother us anymore that you can have multiple names for the same fraction, like 1/2 or 2/4 or 3/6. They're all the same fraction. And similarly, when you're working with congruence classes, you can have multiple names for the same congruence class. So the congruence class that's 1 mod 5 is the same as the congruence class that's 6 mod 5. And actually, it's also the same as the congruence class of -4 mod 5. And so we're working in a situation where we have a well-defined operation, but we have multiple names for the same element. So that's our sort of reminder or quick review, or maybe for some people, an introduction to the integers mod n.